application of complex number to AC series circuit, right? Now, the idea is that the same way we have for series AC circuit, the same way we have application of complex number to series AC circuit, we also have for application of complex number to parallel AC circuit, right? Now, the idea is that you must understand this very well. It is this concept you are going to apply to parallel AC circuit. Now, from here, looking at this subtopic, you will see that we have combination of two topics, right? Which the first one is what? Complex number. The first one is complex number. While the second one is AC circuit. Not just AC circuit, but series AC circuit, right? Series AC circuit. Now, the whole idea of this is that you'll be implementing what you've learned before. The first one is complex number, and the second one is what? AC circuit, series AC circuit. Now, from here, we will be using complex number a lot, and the aspect of complex number that I'll be using is the Argand diagram, the rectangular form of complex number, polar form of complex number, and your Argand diagram. Now, recall under your complex number, okay, by definition, what is complex number? What makes up a complex number? A complex number, when you have a mixture of real parts and imaginary parts, it becomes a complex number. Generally, meaning that, say you have this number, z is equals to 3 plus 4, and z is equals to 3 plus j4. Call this one, call this 2. Now, identify which one is a complex number. Between 1 and 2, which one is a complex number? 2 is a complex number. The question is why? It is a complex number because it has the real part of z and the imaginary part of what? Z. So in essence, we are implementing complex number to this circuit problem. Now, meaning the rectangular form of a complex number, this is it. Now, the polar form, z is equals to r all into bracket cos theta plus j sin theta. So this is what we'll be using. And from here, how do you get a r? By formula, r is given to be square root of b square plus a square. How do you get your theta? Tan inverse of b over a. So we won't be discussing much on this. You already believe that, we already know this, but you can just recall, just take note of this. That's for complex number. Now, for AC series circuit, what we've done previously, we've looked at DC circuit, right? What's DC circuit? By definition, okay, how can we distinguish between DC circuit and AC circuit? Any idea? How can we distinguish between DC circuit and AC circuit? Now, here's how it works. For DC circuit, by the word DC circuit, meaning direct current. DC circuit means what? Direct current. While AC circuit, meaning alternate current. Now, the idea is that for DC circuit, your current moves in one direction, meaning from positive to positive. Similarly, you just reverse the case for alternate current. But let's see what I'm saying. Now, consider this circuit. Say you have this, and this is positive, this is negative. Then consider this also. Now, from here, call this 1, call this 2. Identify which one is DC circuit, which one is AC circuit. One is what? AC circuit. While 2 is what? DC circuit. Now, what differentiates between 1 and 2, meaning AC circuit and DC circuit? We can use a lot of things to differentiate them, but a typical example is the current. Meaning that for this guy, current only move in one direction. But you see this, current move vice versa. Alright, now let's say from this one, let's say we have this diagram also. Let's say you have this. This is TAC circuit, right? This is TAC circuit. Let's say this is 1 prime. Now, 1 and 1 prime, they are AC circuit. But for 2, they are DC circuit. Now, we want to distinguish between AC circuit and DC circuit by current. Now, my question is, what we've learned before, in what manner do our currents move? Is it from positive to negative or from negative to positive? Positive to negative. Now, meaning for case 2, which is your DC, you have your current in this manner, right? this is I, meaning continuously. Let's say your I is still moving in this way, right? Your I is also moving in this way continuously, right? Now from here, this is the, okay, let's say you have this. Now let's draw another circuit diagram. Let's say you have another circuit diagram. Say you have positive, you have negative. Now, is it possible for our current to move in this manner? Is it possible from what you've learned in DC circuit? Why? The question is why? Why? Exactly. Because your DC circuit current always flow from what? Higher potential to lower potential, meaning that your current move in what? Only one direction. One direction, meaning from positive to negative terminal. So by definition, we are not saying that DC circuit means that your current is moving in what? One direction. One direction. Now, can you give me an example of a circuit element that just move in one direction? A diode. A diode move in one direction. So that's the DC circuit. Now what I just want to do is that I'm using this to differentiate between DC and AC. Now for this guy, you know, 1 and 1 prime, they are AC circuits. 1 and 1 prime, they are AC circuits. Now let's say this is your positive, let's say this is your negative. Your current will move in this way, right? Do you agree with me? Your current will move in this way. Similarly, let's say this is your positive, this is your negative. Your current will also move in this way, right? Yes. Now what this means is that current move vice versa. Current can move in any way, meaning it doesn't have a specific polarity. You know, for this guy we said the longest side is the positive terminal, meaning current always move from the what? Positive terminal, constant. But you see this guy, it does not have a specific polarity, meaning for case 1 this might be your positive, negative. For case 2, reverse the case, this might be your positive, negative. Are you getting the concept? So the concept is that for AC circuit, it does not have a specific polarity, meaning your current move in an alternate way. I get what I'm saying? Alternate way. But for DC circuit, it move in what? One direction. Now back to this subtopic. The subtopic is what? Application of complex number to series AC circuit. Then we look at the concept behind complex number. This is what you'll be using, so take note of this. And for your AC and DC, this is what distinguishes between them. Now what are these circuit elements? Circuit elements that you'll be seeing in your DC circuit, and the circuit element that you'll be seeing in your AC circuit. I get what I'm saying? You know, we have a lot of circuit elements. We have resistor, we have capacitor, we have inductor, and give me more examples. We have transistor, a lot, right? To the advanced level, we have a lot of circuit elements. The common one in DC circuit are resistor. True or false? Resistor. When we did Kirchhoff's superposition, Norton's, and a lot, we've been seeing resistor. Meaning the common one as far as DC circuit is concerned is what? Resistor. Now let's see the common one as far as AC circuit is concerned. Meaning when we are giving question, you'll be seeing some circuit elements. Don't let it to be strange to you. It's the common one in AC circuit. Now the number one is we still have our resistor. We have our resistor, and this is how we have your resistor, right? Number 2, we have our inductor. How do you represent your inductor? In a curly way, right? We have it in this manner. Then we have our frequency. Now frequency, what's the unit of frequency? Right? Is this correct? Yes. This is frequency. Your inductor is represented with what letter? L. What's the unit? Henry. Right? Your resistor with what letter? R. What's the unit? Ohms. Now before moving on, we have what we call impedance. Impedance. We also have capacitor. That's correct. We have capacitor. Right? Yes, sir. Now what's the difference between capacitor and a cell, or you say battery? What's the difference? I know by definition. I mean by diagram, by representation. We know by definition, capacitor is a device that stores electrical charges, right? Now while your resistor opposes the flow of current. Resistor opposes the flow of current. Why this guy is your cell. You know, as it is now, this is a cell. When you have more than two cells, it becomes a battery. Now, by representation, what is the difference between cell and a capacitor? Okay, wait. Let's do it this way. My usual way. Call this one and call this two. Now, tell me which one is capacitor, which one is resistor? One is capacitor, two is what? Cell. Why? You observe that for this guy, you have equal terminal, but for this, one is the longest side while the other is the shortest side. So what you are saying is that your capacitor, the two sides, they are equal. The two sides are equal. And if you remember very well, when you did capacitor in year one or year one, when you did capacitor in year one, you said you have dielectric material in between your capacitor. It has a charge, equal and opposite charge. Abi? Yes. So that's it. So this is capacitor. Now from here, we are saying that capacitor is denoted with this what? Symbol. Meaning if I see my circuit having this diagram, it means what? Capacitor. And what's the unit of capacitor? What's the unit of capacitor? Yeah, farad. Yeah, that's correct. Farad. You can see that we are just recalling a lot of things. We're using it a lot. So we have farad, right? You know, I can have my capacitor in millifarad, microfarad, nanofarad, picofarad. Now, take note. When you have 10 raised to power minus 3, 10 raised to power minus 6, 10 raised to power minus 9, and 10 raised to power minus 12. Just remember this surface. This is milli. This is what? Micro. This is what? Nano. Why this is what? Pico. Now, that's it. Then we have 10 raised to power 3 is what? Milli. Yeah. Now, what I just want to say, take note. Now, given a number, you want to convert that number. Let's say we we've solved a question now. And you got your capacitor C to be 0.00003 farad. Now, you just want to write this value in a nicer way. You know, you can express this guy in terms of picofarad or microfarad. Now, let's say you've gotten this value and you want to express this value in nanofarad. How do you do that? Just multiply by 10 raised to power 9. Multiply by 10 raised to power 9. Are you getting me? Just multiply by what? 10 raised to power 9. By the time you multiply by 10 raised to power 9, it means you've converted this value to what? Nanofarad. Yeah, nanofarad. Similarly, if it is picofarad, multiply by what? 10 raised to power 12. Because we use this a lot. Alright, back to what we were discussing. We said we have resistor, we have inductor, we have frequency, we have what? Capacitor. Then, what else? Yeah, impedance. I was saying something about impedance. I said, by definition, what is impedance? Okay, what is the difference between impedance and resistor? Okay, impedance is the total resistor to the flow of current in an AC circuit. We said we have DC circuit, we have AC circuit. Now, when it comes to AC circuit, you'll be using the word impedance. When it comes to DC circuit, you'll be using the word what? Resistor. Now, here's how it works. Resistor and impedance, they are synonymous. They are what? Synonymous, but used in different concepts. Now, for resistor, as I said, it is the combination of your what? Resistor in your AC circuit. You know, this resistor of a thing that we are saying, you have capacitive reactance and what? Inductive reactance. You can term capacitive reactance as resistor, true or false. Similarly, inductive reactance. Now, say you have a circuit combined with a resistor itself and capacitive reactance. What do you call the total circuit? What do you call the total resistor? Impedance. Similarly, say you have a resistor and inductive reactance. What do you call the total resistor? Impedance. That's how it works. So meaning that by definition, impedance, it is the combination of the total resistor in a circuit. Meaning it varies. Case 1, you might have your resistor and capacitive reactance. Case 2, you might have your resistor and what? Inductive reactance. Now, take notes. Don't worry, this course is interesting. This subtopic is actually interesting. Don't worry. Let's continue. You will see why I need to do emphasis on this, because by the time you start solving, you believe that you already know a lot of things. So that's why I just need to brush it up. Are you getting me? So don't be tired. Don't worry, when you start solving, you see that it's very interesting. Yeah, let's continue. Now, number 5. We said we have what? Impedance, right? And what's impedance denoted with? Z. Impedance, right? Denoted with what? Z. Meaning that as far as this subtopic is concerned, we said your impedance might be of two types. When you have your resistor and your what? Capacitor. When you have your resistor and your capacitor. Then 2, when you have your resistor and what? Inductor. Now, meaning let's say Z of inductor, right? I get what I'm saying. Well, since we said inductor is represented with L, so let's say since we said inductor is represented with L, so let's say impedance of what? Inductor. This is the formula, meaning you have R plus what? XL. You know, this is what we know. This is what we are learning now. But when now you are bringing this idea to complex number, this impedance, you represent your impedance in form of complex number. You get what I'm saying? You represent your impedance in form of what? Complex number. But you see how it works. Now, this is impedance, right? This is the impedance of inductor. Now, the impedance of capacitor, that would be what? Who can tell me? R plus R minus, okay? R plus XC. Alright, now R plus XL, R plus XC. Then lastly, before we move on, by formula, what is XL? XL means what? Inductive reactance. XL means inductive reactance. XC means what? Capacitive reactance. Now by formula, let's see. By formula, take note. XL, what's the formula of XL? 2 pi FF. What's the formula for XC? 1 over 2 pi FC. Alright. So this is what we'll be implementing as far as this subtopic is concerned. By the time you know this, you are good to go. Alright. Alright, impedance for the 3 resistors. Yeah, then impedance for, meaning when you have your resistor itself, when you have your capacitor, and when you have your inductor. So this is the meaning that Z open bracket XC, let's say XC to XL. You see the proper representation of this when we start the topic, equals to R plus all into bracket, right? Is that correct? When we start, it will become XL minus XC. Yes. All right. So just take note of this. Any question before we move on? Any question? No question. We said that we have application of complex number to series AC circuit. This is what we'll be implementing as far as complex number is concerned, and this is what we'll be implementing as far as AC circuit is concerned, in brackets, series. All right.